Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss linear diatomic vibrations. Let's begin. In the previous video lecture, we have already discussed about linear monoatomic vibrations. In case of monoatomic, we prefer a single type of atom is present at the primitive basis of that entire crystal structure. But here we have to choose combination of two atoms that present inside that of primitive basis throughout that of crystal. Therefore, its name as diatomic. Let us take case of one dimensional diatomic lattice which has two atoms per primitive shell. Let an example of sodium chloride. Two kinds of atom, one is sodium, another one is chlorine. The combination of sodium chloride or the diamond structure. As it contains two atoms, let the mass of the two atoms, one is m1 and another one is m2, and mass of m1 is small than that of mass of m2, and the distance in between these two nearest neighbors be small a. Small a, distance in between these two nearest neighbors atom. And suppose the atoms are arranged in x axis, as we prefer the linear, that is in one dimensional situation. So we prefer the atoms are arranged along x axis and these atoms are placed at that of lattice sides 2n minus 3, 2n minus 2, 2n minus 1, 2n, etc. 2n plus 1, 2n plus 2, 2n plus 3, like this. And these positions, as we taken two kinds of atom, one mass is greater than another, so the atoms having smaller mass are placed at even numbers. Smaller mass placed at even numbers sides. These numbers are dedicated to 2n even, 2n minus 2 even, 2n minus 4 even, like that of 2n plus 2, 2n plus 4. These are the even sides. At even sides we place the smaller mass atoms, whereas the atoms having larger mass are placed at odd number sides. Larger mass are placed odd numbers like 2n minus 2, 2n minus 3, and so on. Here 2n plus 1, 2n plus 3, and so on. And here we assumed there are supposed to be same as that for monoatomic lattice, except here we choose x2n represent the displacement of 2n side atom. We can show it in figure. In xy plane, one dimensional lattice along x direction, the atoms are one is small, another one is large. At the 2nth position, it is 2n minus 1th position, that atom at 2n minus 2 position, this atom 2n minus 3 position, this atom 2n minus 4 position, like this. N minus 5th position, 2n plus 1, 2n plus 2, 2n plus 3, 2n plus 4, 2n plus 5. The smaller one is M1, that is the smaller one, M1. The larger one be the M2, and the spacing in between these two is small a, and that is present at a distance of Na from that of origin, and these are connected by the springs. Smaller masses are placed at even numbers, smaller masses 2n minus 2, 2n minus 4, 2n plus 2, 2n plus 4. Larger masses at odd positions, 2n minus 1, 2n minus 3, 2n minus 5, 2n plus 1, 2n plus 3, 2n plus 5. These are the positions of larger masses. These atoms are present like this manner in that of equilibrium state. In equilibrium state, but when we applied an external force, then these lattice points are vibrated, or when we increase the temperature, automatically the atoms are vibrated. During that of strained state, the atom that present in 2nth position displaces as x2n, and atoms present in that of 2n minus 1th position, it displaces as x 2n minus 1 and 2n plus 1th position atom displaces x 2n plus 1, that be the strained state situation. Strained state situation. Now we have to show what be the equation of motion of that of atoms having that of strained state situations, or in other words we can say what be the net force acted upon these atoms. The net force acted upon atom M1, that force equation mass into acceleration, that is the second order rate of change of displacement d2 x2n dt square is equal to the net displacement at M1, the displacement here alpha x 2n plus 1 plus x 2n minus 1 minus 2 x 2n, the net force on that of M1 due to that atom and also due to this atom, two neighboring conjugative atoms, what kind of force executed on that of atom M1, that will be the net force, that net force is expressed. Next, the net force acted upon atom M2 in similar fashion, mass into acceleration, second order rate of change d2 x 2n plus 1 its displacement dt2 is equal to alpha, and total displacement means what be the force applied on that of particle M2. Here is the particle M2, it is x 2n plus 2 plus x 2n minus 2x 2n plus 1. So, the net force on M1 and net force on M2. Here the term alpha, that be the spring constant, or we can say the interatomic force constant. Equation number 1, equation number 2. Here alpha, the spring constant or interatomic force constant. And the solution of equation number 1, solution of equation 1, solution of equation 1, x2n is equal to a e to the power I 2kna minus omega t, the equation number 3, and solution of equation number 2, solution of the differential equation number 2, it is x 2n plus 1 is equal to b e to the power I 2n plus 1 ka minus omega t. Equation number 4. Here since we consider the diatomic lattice, so two masses are not identical, so their amplitude of vibrations are taken to be different. So here the amplitude of vibration is A and there will be the amplitude of vibration is B. In diatomic lattice, two masses are not identical, so their amplitude of vibrations are taken to be different. Therefore, for equation number 3 we use the amplitude A, and for equation number 4 we use the amplitude B. Next, since both the masses are vibrating in identical manner, the frequency of both the atoms is taken to be same, is taken to be same. Here omega, there will be omega. Okay, it's an important point. Since masses are not identical, their amplitude of vibrations are taken to be different. Since the masses are vibrating in identical manner, the frequency of both of atoms taken to be same. Now we have to differentiate equation number 3 and equation number 4 twice. So we have to obtain d square x2n divided by dt square and d square x2n plus 1 divided by dt square, and these two values are put in equation number 1. Now differentiating equations 3 and equation 4 twice and substituting the respective values in equation number 3 and equation number 4, putting that value of equation number 1 and equation number 2. We get here we put these values in a direct manner as we taking the linear monoatomic lattice vibrations. That will be the expression for linear monoatomic lattice vibrations. When we obtain the second order differentiation and putting that values, we have this form of equations. Same thing we applied here. So, equation 1 now becomes minus m1 omega square a is equal to, just relate to one dimensional lattice vibration. What we obtained? Alpha will into this much, that much. So, alpha will into e to the power I k a plus e to the power minus I k a here we chosen b minus 2 alpha a, last term is 2 alpha a. This is monoatomic lattice vibrations. We just relate it due to put these values in direct manner. That will be equation number 5. Next, similarly, putting its second order differentiation to that of equation number 2, what we obtain? Minus m2 omega square b is equal to alpha whole into e to the power I k a plus e to the power minus I k a whole into a minus 2 alpha b, equation number 6. And we know that e to the power I k a plus e to the power minus I k a as 2 cos k a, e to the power I k a plus e to the power minus I k a is equal to 2 cos k a. Now, that values we can replace in that equation number 5 and equation number 6. Therefore, these two equations further written as, show that equation 5 and 6 can be written as and taking that value to this side and the negative sign is multiplied, so that equation 5 becomes 2 alpha minus m1 omega square a common minus 2 alpha cos ka into b equal to 0, and rearranging equation number 6, that to this side and negative is multiplied, so that equation becomes minus 2 alpha cos ka into a plus 2 alpha minus m2 omega square will into b is equal to 0. From these two equations, if we choose its solution in terms of omega, we have to take in its determinant form. From above two equations, we have two alpha minus m1 omega square minus 2 alpha cos ka minus 2 alpha cos ka 2 alpha minus m2 omega square, determinant as 0. Now solving the determinant, or 2 alpha minus m1 omega square whole into 2 alpha minus m2 omega square minus that multiplication as 4 alpha square cos square k is equal to 0, or expanding these terms as 4 alpha square minus 2 alpha m2 omega square minus 2 alpha m1 omega square plus m1 m2 omega fourth minus 4 alpha square cos square ka is equal to 0. Rearranging the terms, first the term as m1 m2 omega fourth minus 2 alpha omega square as common, we have m1 plus m2 plus 4 alpha square as common, 1 minus cos square ka is equal to 0, or now dividing m1 and m2 on both sides, we obtain omega fourth minus 2 alpha as m1 plus m2 divided by m1 plus m2 of omega square plus 4 alpha square sin square ka divided by m1 m2 is equal to 0. Look at that particular equation, that is equation in the form of ax square minus bx plus c is equal to 0. This is a quadratic equation in terms of omega square. This is a quadratic equation in omega square. quadratic equation in omega square. So its solution the solution is we can have its solution as omega square solution omega square is equal to minus b plus minus b square minus 4ac divided by 2a. In a there is 1, so in these two terms we taken 2 as common, and numerator and denominator side 2 is cancelled out. I write that solution as alpha. So that term as m1 plus m2 divided by m1 into m2. So m1 divided by m1 into m2, m1 cancel out, it will be 1 by m2 plus m2 divided by m1 m2, m2 cancel out, so 1 by m1. So in that bracket we have alpha whole into 1 by m1 plus 1 by m2 plus minus, again same thing, alpha is common throughout that of root term, inside that of root 1 by m1 plus 1 by m2 whole square minus 4 sin square ka divided by m1 m2. That the solution of this quadratic equations, equation number 7. So it has two roots, it has two roots, one is positive, another one is negative. So omega plus positive root, we chosen the positive one, so it will be alpha 1 by m1 plus m2 plus alpha whole into, in that of root over 1 by m1 plus 1 by m2 whole square minus 4 sin square ka divided by m1 m2 in the positive one, and for negative one omega minus square as alpha 1 divided by m1 plus 1 divided by m2 minus alpha in that of root over term 1 by m1 plus 1 by m2 whole square minus 4 sin square ka divided by m1 m2. One root, this is another root. These expressions, these equations are called the dispersion relation. Dispersion relations for one dimensional diatomic lattice vibrations. One dimensional diatomic lattice vibrations. These are the dispersion relations. So here with the help of this video lecture we understand the concept of linear diatomic vibrations. These are some points we write for linear diatomic vibrations. Mathematically we show the net force on m1 and m2, its solution, why the amplitudes are different and the frequency will be same, and next putting its corresponding values we obtain a quadratic equation in terms of omega square. So it has the solution and having two roots, one is positive one, another one is negative one. These equations are basically known as the dispersion relations. That with the relation in between omega and k is known as the dispersion relation. These equations are the dispersion relations for one dimensional diatomic lattice vibrations. So with this useful and informative notes, let me wind up this session. Thank you.